All right, so let's fill this in. In terms of Ka value, what can we say about the Ka value of a strong acid? Large. And for weak acid? Small. Okay? Strong acids have large Ka values, very large. Weak acids are small. What about equilibrium position of the dissociation reaction? For strong acids, what does the equilibrium favor? The conjugates, or we could say equilibrium favors the right, the products. What about for weak acid? Well, it can be to the left. So we could say, for example, that a strong acid is going to favor H+, a weak acid is going to favor HA. And when we say H+, that's the same thing as H3O+, right? We'll use that interchangeably, and I won't always necessarily remember to tell you that conversion, but H+ and H3O+, same thing. H+ aqueous, I should say. All right, what about the equilibrium of concentration of H+ versus the equilibrium concentration of HA? Okay? In the case of a strong acid, the H+, concentration of H+, is greater than the concentration of HA. Okay? And we might even say much greater than. What about for a weak acid? The opposite will be true. Concentration of H+ is going to be much smaller than concentration of HA. All right, now this one we're going to have to kind of wrestle with a little bit to figure out. The strength of the conjugate base versus water. Now, a strong acid is going to make what kind of conjugate base? A weak. Now, if the acid is stronger than water, what do you expect will be true about the conjugate base compared to water? It'll be a weaker base than water. And what about for a weak acid? If the acid is weaker than water, what do you expect you can say about the base? It's going to be a stronger base than water. Okay?
So if it's stronger than water, does that mean it dissolves more easily than water?
No, it doesn't have anything to do with solubility. What it has to do with is if there's a free proton floating around out there, what is it going to go to preferentially? Is it going to go to this preferentially or to water preferentially? If that extra proton is more inclined to go to the conjugate base than it is to water, that makes it a stronger base. Because that's what a base is, right? It's a proton acceptor. Okay, we are making great progress here. And as noted on here, this same table is in your book on page 627. If you wanted to make a note of that, that might be helpful. All right, let's see what we need to talk about next. Oxyacids. So far. What is an oxyacid? Well, it contains oxygen. Specifically, an oxyacid is an acid where the proton that comes off, what we call the acidic proton, is attached to an oxygen atom. other than the halogen acids and things like that, like H2S, hydrosulfuric, hydrocyanic, potentially, most acids are oxyacids. Most acids are, arranged in such a way that the hydrogen that comes off is attached to an oxygen. And we will talk about that not today, but in a later conversation. So, oxyacids are acids where the acidic proton, in other words, the proton that comes off, is attached to an oxygen atom. Let's show you a couple of these so that you can kind of see what they look like. Perchloric acid. I think it's always interesting to draw the dot structure for perchloric acid so you can kind of see what happens. If you draw the chlorine first, okay? Chlorine has 1, 2, 3, 4, 5, 6, 7 electrons, right? 7 valence electrons because it's a halogen, it's in group 17. Where are you going to put an oxygen on there? The most immediately obvious place is to put it right there. You can put it's 1, 2, 3, 4, that one's already full, 5, 6. That's it. Now, you know a little bit about the halogen oxyacids, don't you? You know that each of them has a progression. You have this. If we were to just slap the last proton on there, or the last electron on there right now, we could put it right there. What would that ion be called? So it's got a chlorine, it's got an oxygen, and the black one represents one additional electron, so it's got a -1 charge. ClO minus, which is called? No. What is it? Chloride is close. It's the one just below that. Hypochlorite. Okay? So this ion, as written, would be hypochlorite. To get from hypochlorite to chlorite, you just have to put another oxygen atom on there. Well, where would it go? I don't know. How about right here? Now, the fact that this oxygen can attach without donating any electrons of its own, it just uses the 2 electrons that are already in chlorine. Do you remember what that's called?
Coordinate?
It's a coordinate bond. Coordinate covalent bond. Good. Okay. And then we could do a third one up here by the same mechanism, and a fourth one down here the same way. That is the perchlorate ion. And the easiest way to come up with the formula is to just do hypochlorite first and then slap the other 3 oxygens on there wherever they'll fit. Now, where would a hydrogen go in here? Well, how about down here where we added that last electron? Okay? This hydrogen is acidic. That means this is the one that comes off. Well, in this case, there's not a lot of other options, are there? There's only that one hydrogen in there. But this is the acidic hydrogen. That's the one that separates.